Okay, so I'm here today in order to present you a research work about diazonium cation exchanged clay synthesis characterization and reinforcing properties of clay polymer nanocomposite. So in this talk, we will give you a generality about clay polymer nanocomposites. Then we would like to concentrate on different steps of preparation of polyaniline tiny with diazonium salts, exchanged clay, and discuss the results of the product. Firstly, what is a nanocomposite? A nanocomposite is a multi-phase material in which, in contrast, in microcomposites, one of the phases has 1, 2, or 3 dimensions of less than 100 nanometers. So, or the composite phases have nanoscale distances between them. So nanocomposites can be classified into different groups based on various criteria. Generally, nanocomposites are categorized according to their dimensionality and matrix phase. So nanocomposites consist of one or more discontinuous phase of distributed in one continuous phase. In our work, we are interested about polymer clay nanocomposites, which organic, inorganic nanocomposites. So PCN are the most important nanomaterials of the current decade with the wide range of applications. We have montmorillonite, sepiolite, laponite, bentonite, and magnetite are the main classes of clay used as reinforcements in polymer nanocomposites. There is more than 20 years have passed since researchers invented PCN, in which only a few weights % of silicate are randomly and homogeneously dispersed in the polymer matrix. Toyota's patents accepted the PCN show excellent mechanical properties, enhanced modulus and dimensional stability, flame retardancy, improved scratch and mar resistance, superior thermal and processing properties compared to those of pristine polymers. To date, the main challenge in PCNs is the chemical composition of the layered silicates and their ability to be modified by organic or inorganic modifiers. Through such modification, it is possible to incorporate hydrophobic properties into clay particles such that they can be dispersed finally in the polymer matrices, and the modified clay enhances the mechanical properties, thermal properties, and barrier properties of polymer clay nanocomposite. Most importantly, the amount of clay in PCR influences the crystallinity of polymer and the mechanical properties. In general, there is 3 different routes are followed for the preparation of polymer clay nanocomposites. There is solution intercalation, melt processing, and in-situ polymerization. And it is possible to obtain minimally 3 different types of shifters. And that depends on the PCN's preparation and the clay modification. We can obtain microcomposites, intercalated nanocomposites, and or exfoliated nanocomposites. As you see in the screen, the shifter confirmation of different types of PCNs is usually done by X-ray diffraction and transmission electron microscopy. Then, in the conventional one, the clay is dispersed at best only in the form of liminally particles or agglomerates, and without penetration of polymer matrix into clay galleries. In the second one, in the intercalated nanocomposite, the interlation and the insertion of the polymer matrix into the layered silicates into the layer silicate treated occurs crystallography regular way via interlating polymer chains and the silicate layer. And in the third one, exfoliated the nanocomposite. The individual clay layers are randomly separated in a continuous polymer matrix by an average distances that depends on the clay loading. So there is an increasing trend in global marketing of the polymer clay nanocomposites, and some of them are presented in the image. The PCN's applications area includes in different fields, including aerospace, defense, photovoltaic cells, photovoltaic solar cells, gas sensors, automotive industry, etc. So, as you see on the screen, our topic today is polyadenine magnet clay nanocomposites elaboration, and this work is divided into 3 steps. We have diazonium cells preparation, modification of magnets Na with the diazonium cells, and the in situ polymerization of nanocomposites. The N-dimethyl aminobenzene diazonium tetrafluoroborate salts was prepared by added 1 equivalent of tert-butyl nitrate to an acidic aqueous solution of HBF4, 50% of the corresponding aniline. The solution was stirred at 0 degrees Celsius for 1 hour, and then acetone was added to dilute the former solution. Finally, the diazonium salt was precipitated with cold diethyl ether. The final powder was filtered and stored at fridge for the next step. The second step is the modification magnet with diazonium salts. For that, a aqueous solution of DMS salt was poured into an aqueous solution of clay. The reaction occurred instantly, and a swollen solid precipitate. The product was filtered, dried, and stored for the next experience. As you see in the screen, the formed precipitate is visible with the naked eye. The goal of this step is to get a modification surface that we need to reduce nitro group to amino group. For that, the DMA clays were added into a aqueous solution of tin stirred at 0 degrees Celsius for a few minutes. Then an acidic aqueous solution of HCl was poured. The mixture was stirred for 24 hours at 70 degrees Celsius. The product was washed several times and dried and stored. The third step and the final step is a synthesis of the nanocomposite. So we have for that the nanocomposites were synthesized by in situ method. We have a quantity of organomodified magnets was added to aniline monomer in a flask, followed by an oxidizing solution of the ammonium persulfate with aqueous solution, with acidic aqueous solution, and the mixture was left stirring for 24 hours at 0 degrees Celsius. The product obtained is in the form of black powder, was recovered by filtration, followed by washing with distilled water and methanol to remove unreacted monomers, and dried in oven at 60 degrees Celsius for 24 hours. So, what about our research and discussion? We initiated initiated with the FTIR. As you see on the screen, the FTIR spectrum of diamond, there is a characteristic bands of the diazonium salt powder are known to be in the region of 3,350 and 50 and 1,400. The presence of two strong intensity bands at 1354 and 15 and 1545 centimeter correspond to this to the symmetric and asymmetric of the micro groups stretching vibration respectively. Yeah. So whereas the intensity one at 2,300 centimeter is asymmetric to the NN stretching vibration. The structural OH bending mode in magnet diamond absorbs between 700 and 950. So, and shows a series of discrete peaks that indicate the cation composition in the octahedral sheet. So the OH bending mode of aluminum OH absorbed groups absorbs near to 900 and 920. There is the OH bending of magnesium aluminum OH absorbed near to 800 and 835. After the modification with the nitrobenzene diazonium cell, the spectrum of magnet diamond shows different characteristic peaks that of diazonium salts. Diazonium salts presence in magnets, particularly the stretching NN. It is important to know that it disappears over the nights of drying in oven at 16 degrees Celsius, resulting of an efficient deazonation process. Yeah. So furthermore, the reduction of nitrobenzene group into amino group on the diazonium diamond was for facilitate the cationic exchange reaction and the grafting of aniline monomers on the surface of magnets emanations. Yeah. Sorry. We talk about the approach of nanocomposites. Yeah, the intercalation of polymer with the clean materials was confirmed by FTIR spectrum that the presence of polyaniline is justified by the presence of the main peaks. The characteristic peaks of for well-doped Pani cell at 1567 and 14 assigned to C-kinoid ring stretching, and at 1492 assigned to CC stretch benzoid ring stretching. The band at 1297 attributed to CN stretching vibration in polaron from the polyimmelaradyl cell. So moreover, the presence of two peaks around 3,000 and 3,263 and 3,626 are assigned to symmetrical and asymmetrical elongation of the NH group. Going to the UV visible results of our product, the UV visible absorption spectrum of polymagnet diamond reveals three major characteristic peaks. The absorption of 206 nanometer is attributed to the transition of electron form of the highest occupied molecular orbital HOMO to the lowest occupied molecular orbital LEMO, PP electronic transition. The absorption around absorption around 271 nanometer, and the third one at 374 are ascribed to the polaron P and P polaron, benzenoid and fucinoid excitonic transition, respectively. So this may be due to the strong interaction between magnet diamond and the polymer chain, or the increase in the conjugated unsaturated bonds. The change in the layer spacing of magnet clay after ion exchanging and with diamond was found to increase from 12 angstrom to 13 angstrom in the magnet's diamond. In the case of the nanocomposites, the repetitive multi-layer structure is well preserved, allowing the interlayer spacing to be determined. So the intercalation of the polymer chains usually increases in the interlayer spaces in comparison with the spacing of the modified clay. Sorry. So the TGA curves for magnet diamond and tiny magnet diamond. The first one loses below 100 degrees Celsius, probably a result of the release of water by all the samples. Gradual weight losses were observed in the temperature range of 200 to 640 degrees Celsius and above 450 degrees Celsius for the tiny magnet diamond nanocomposites diluted to determine the composition of tiny biker bound chains according to previous works. Smectic type clay has been found to improve the thermal stability of the polyaniline. Here we have the micrographs of tiny magnets NA. Exhibit nanocomposites, exhibit more ordered and dense structure. B for magnets. For the nanocomposite tiny magnets NA, it was B. So exhibit more ordered and dense structure after intercalation of sodium into the magnet layers. The structure of magnets, tiny magnets, and nanocomposite had changed and displayed on an oriented fracture, probably due to the orientation of the crystal layered into the polymer matrix. It is evident that the surface of the nanocomposite tiny magnets diamond is different than the observed in the case of tiny magnets and nanocomposite. It has a typical plate-like morphology and is adorned with blasonium. In addition, this indicates that in situ annealing polymerization was done on the surface and into the nanoclay galleries. What about electrochemical response? So the successive cyclic voltammograms show three potential peaks during the positive scanning, anodic and the cathodic scan. These peaks correspond to different states of oxidoreduction of polyaniline. The first redox couple is the most reversible. This is justified by the value of delta EPE, which is very close to 60 millivolt. It may indicate that the presence of oligomers or degradation products from the presence of orthocoupled polymer segments embedded in the polymer matrix. The second redox peak corresponds to the transition from leucoemeraldine to emeraldine on the forward scan, and on the background, backward scan back to local emerging can be seen. The third redox is redox peak corresponds to the transition from emeraldine to pernigraninine. While on the reserve scan, the reduction from pernigraninine to emeraldine is observed. So regarding the results, it was found that electrochemical behavior of the nanocomposites is completely reversed and showed that the panimagnetic nanocomposites are electroactive. So we can go to the conclusion. The panimagnetic nanocomposites were successfully prepared by in situ polymerization method in the presence of ammonium persulfate as oxidant as well as dopants. Magnetically was modified by cation exchange reaction by sodium by diazonium salts with intercalated the silicate layers and reacted on the surface of the silica platelets within the interlayer spacings. From the XRD patterns and the SAM photographs, we observed the structure and the compact morphology with the cation exchange of diazonium salts and polyaniline in magnetically. And based on the TGR results, we found that the thermostability of panimagnetic diamond nanocomposites are relatively improved by improved through intercalation. The good electrochemical response has been observed for polyaniline grow into magnetic diamond, in which the cyclic voltammogram shows broad anodic and cathodic peaks that consist on the overlapping of redox process. This indicates that the aniline polymerization into the magnetic diamond is electroactive. Therefore, this surface modification process opens the way for a large number of applications requiring not only polyaniline magnetic diamond nanocomposites, but also other types of polymer matrix with modified fields. And that brings me to the end of my presentation. Thank you for listening.
I think it's really comprehensive work related to your topics on diazonium calcium extent clay, synthesis, characterization, and reinforcing properties. I noticed that we still have a couple of minutes for question and answers. Is there anyone want to ask from the Zoom or also from the person session? Anyone? Okay, so I think that maybe comes from me, Dr. Fatima, and I'm really enjoying your presentation, but previously I have kinds of work that related to it, polymer synthesis, but I have a problem during the enforcing of these properties. And maybe you can share your experience. Is there any obstacle or other factors that need to be maintained during reinforcing properties on polymer, especially on nanocomposites?
Please, have you asked me?
Yeah, we can hear you.
I don't hear you clearly.
Okay, yeah. What I want to ask you is what kind of things that we need to maintain during your reinforcing properties on nanocomposite? Can you hear me right now? Hello?
Yes, sir, I have a mistake to hear you.
Hello? Dr. Fatima?
Yeah, can you send me as a chat because I can't hear you.
Okay, yeah. Okay.
Yeah.
I think I can do it after your session if it's necessary. Okay. Thank you so much, Dr. Fatima, for your participation in this ICAMT conference, and hopefully we can learn a lot from your work. And thank you for sharing with us. Okay, ladies and gentlemen, we will move to the next session, which is our contributors. Give me a minute. Okay. After the invited speakers, we will have Mr. William Harrison Minitio from University of Indonesia. He will deliver a topic related to the recent development of calcium doping and perovskite active layers and transport layers toward high efficiency and stability. And we have Siri here, Mr. William, and you can start it right now.
Okay, may I start now?
Yeah, sure.
Okay, thank you very much. Please let me know if you have seen my screen.
Yeah, we have seen it clearly.
Okay, thank you very much for your confirmation. Okay, thank you everyone. Please introduce myself. I'm William from University of Indonesia, and now I would like to explain a little bit about my review paper regarding the recent development of cesium doping in perovskite active layer and transport layer toward high efficiency and stability. With the authors, I'm on behalf of my professor in here, Ahmad Herwadiwono, Nofrijan Sofyan, Donata Dariswara, and etc. Widodo Wahyu Purwanto. And for the outline, I would briefly explain about the abstract, and then next to the introduction, and after that, it's regarding efforts in enhancing performance in active layer by cesium cations. And next, I would like to explain the same, but in order of cesium compound. And after that, the last is efforts in enhancing performance in transport layer. And after that, I would like to get into the conclusion. And the last is references that I have used. So basically, from the abstract, is the perovskite materials is basically considered as a next generation solar cells that basically have a good potential to replace current silicon-based solar cell. And as we know that current biggest market share of the solar cells that is used is silicon-based. And basically, regarding this perovskite material, it has a fast improvement and efficiency and stability from 3.9% until 25.5% in such a few decades. So this is have a huge development there. And several of disadvantage of these perovskite materials is due to unstable phase and many crystal defects when fabrication. And it's considered toxicity because it has lead materials in here, in there, and also susceptible to the cell degradation due to humidity and the ultraviolet exposure. And there is many methods and engineering have been made to overcome this advantage. And one of them is doping, which is a method that inducing elements or compound that could receive better performance after being induced. Basically, regarding doping in the perovskite solution, perovskite materials, it could be a promising method because it would be alter the interface between the electron selective layer and the strain of the perovskite structure, and thus it would improving higher efficiency and improve operational stability. And also, there is many types of compounds or elements that could be used to dope the perovskite layer. But one of them that is quite well known is cesium. Cesium is a compound or cation, or it can be formed in cations or compound that can be applied in active layer, transport layer, or as an additive. And basically, in short, this article or my presentation would review a recent cesium effort made by researchers to be induced inside perovskite solar cells and their effects toward high efficiency and operational stability. So basically, renewable energy is promising way for the future and for us to obtain such a clean and environment-friendly resources. Despite the dependency and the increased fossils and oils price. Pollution scarcity is considered a problem when in hand, and action must be taken in order to achieve 100% full utilization of renewable energy. And there is many types of renewable energy utilization, such as geothermal, wind, water stream, etc. And one of the widely known renewable energy is solar energy. And many efforts has been made in order to improve the solar energy, such as in solar panels and solar cells recently, and in order to obtain better performance of energy harvesting resources. So basically, as explained earlier, the perovskite solar cells is one of type of the materials for perovskite solar panels that would be a promising candidate for the next generation solar cells. And what you see in the right side here is the typical structure of the perovskite solar cells. But currently, this solar cell is still on the research area, but not many of them has been commercialized. So as you can see in here, the structure would be start from the glass and Florentine oxide as a conductive glass, and then there is a titanium dioxide as transport layers, and there is also the core of the perovskite solar cell itself that would generate charge, the hole and the electrons, and after that we have a whole transport layers, which is spiral method, and a transparent and the electrodes. So as I have said earlier, that this solar cell have disadvantages or this application compared to other solar cells. Basically, that the lead element could be toxic on the production or even an operational surface. And if it's not sold properly for the human environment, it could be have a degradation of performance because it been exposure to moisture and UV radiation at the same time. So as you can see in here, this is the perovskite crystals, which is MaPbI3, and in the presence of moisture and thermal and UV, it would degrade, and the crystals would not perform. So and this is would degrade into two kind of compounds, and this would not give a good performance to solar cell itself. And there is many methods that have been done in order to improve the performance of these solar cells. Some researchers take efforts in finding optimization and analyzing parameters and process. And some researchers are also changing both perovskite types and transport layer types and via light management, etc. And one of the methods known to improve this performance is by doping. Doping itself could be many types, could be lanthanum, europium, lithium, etc. But one of them that is started to be researched is cesium. Cesium is one of many elements that is shown to provide improvement of photo stability and structure stability of perovskite. And there is a reason why cesium has been selected as a doping media. The first one is as cation. Cesium would replace the A-side cation, such as methylaminium, formamidinium, etc., and decrease B and X bond length. As you can see in here, basically this is the typical perovskite crystal structure, and basically this is the methylaminium as a precursor. And what we are going to do is we are going to replace partially the precursor of the cation with the cesium cation and see what it going to change or alter the performance. So basically, when we're talking about the cesium cation doping, there is some efforts to make better performance and stability by cesium cation doping. As you can see here, there is several researchers that have made their efforts in order to increase the performance of the perovskite solar cells. And basically, they have a similarity in the idea, which is written as below. They mostly adding various range of percentage cesium into the perovskite material, mostly into the perovskite with methylaminium based. So they were doping the cesium into the methylaminium with iodide based material with the percentage of mass percentage of cesium starting from 5% until 100%. And they perform the characterization by using XRD, UVVs, and SEM to see the grain size, the performance, and also the stability of the perovskite solar cell. And the results in here that doping cesium cation would give a better absorption, bigger grains, and better power conversion efficiency. with the cesium doping perovskite solar cells. And some papers recommended the mass percentage doping of 5 until 10% in order to obtain the better performance of perovskite solar cells. And also there is some efforts, another from doping some percentage of cesium. So I would like to explain about the efforts that have been made by another researchers, such as in these three researchers. This is from different group, but the idea is mostly quite the same. So the effort is adding the various range of percentage of cesium into the same methyl ammonium and formamidinium. So they use triple cation in here, which is cesium, and the base precursor methyl ammonium, and the second base precursor formamidinium precursor with the range of 5% until 14%. And there is also an effort from other researchers that adding specific percentage of cesium and also addition of another cations such as kalium and natrium. Research that is obtained is mixing precursor with methyl ammonium or formamidinium consistent with the previous result. So there is research that has been made by doping cation, and this doping with MA and FA mix precursor would optimize the performance of the perovskite solar cells. But again, the mixing between the precursors, which is MA and FA precursors, seems not to give effect on the power conversion efficiency, because we know efficiency is the number one on the performance of the perovskite solar cells. And also addition of more precursors should be consideration for the cost. Especially when we would like to getting into the commercialization stage. And there is also another efforts from the researchers, as you can see in here from Kim et al. They and the team perform cesium doping by 10% more via sequential deposition method. So they do not synthesize together, but they drop the cesium solution drop by drop after the perovskite layer has been formed, until the another researchers like Hu et al. That perform cesium doping and utilization of gamma aminobutyric to tune the lattice strain. These researchers has given the similar results, and the conclusion is cesium can be used in many advantage for stability other than increasing performance and available to different manufacturing process. And there is also in efforts from another researchers also regarding doping cesium, but not in the form of cation, but in form of compound. So maybe on the carboxyl cesium, or maybe in the acetate, cesium acetate form. So as you can see, there is researchers in here that made efforts. The first one, they tried to use cesium trifluoroacetate to reduce trap by interaction carboxyl into the PBI framework. So this is the function of the trifluoroacetate ions, basically to interact with the perovskite structure as also. And also for another researchers, there is using cesium chloride, cesium acetate, and cesium iodide to suppress better crystallization and suppress defect density. As we know that one of the good performance from the perovskite solar cell is a good crystallization and uniform crystals. And conclusion that we can get from here is cesium in form of compound could either acetate, trifluoroacetate, or etc. like chloride. It could also bring advantage by reducing stress density, crystallization, and etc. And for the last one, there is efforts from doping cesium into the transport layer. So apart from the perovskite solar cells, perovskite structure, we would like they have some efforts to modification the transport layer by doing some cesium compound. So the efforts in here like divided into two different groups. The first group of researchers have the efforts to doping cesium acetate and cesium carbonate to the ETL, electron transport layer, or in here we could know that zinc oxide or titanium oxide, and it would give implication to reduce carrier recombination in the surface interface and reducing pinholes. And there is also efforts that using cesium nanotube and nanorod for better absorption and could prevent recombination. And the result is cesium that also has advantage in modification and engineering, but not in also perovskite layer, but also in electron transport layer, both in the compound type or in nanostructure. So we are getting into the conclusion of most of the role of the cesium. So the first one is, until now, there is many efforts has been made in order to enhance performance and perovskite solar cells. In order to one step closer and scale up commercialization, it's a huge challenge to overcome and reveal many effects engineering every part of the solar cells. And also cesium doping is one of the example that begin to be studied, but there is a lot of understanding and mechanism that is not totally been well understood. But some conclusion that can we gather from these efforts from the researcher is, firstly, the cation of cesium can be used to stabilize the crystallization process and change crystal structure, reducing strap state and density, and one method of engineering of the band gap through the alteration of the percentage of the cesium doping. And also, it seems that 5 to 10% doping is suitable due to maximum absorptance obtained and still on the tunable absorption. And for the recommendation, recommendation is basically to make other emerging research for the next research is trying to emphasize the study of three cations such as Ma, Fa, and cesium, because not many research has been found on this development of three cations in one perovskite solar cells, and try to understand the better for stable perovskite solar cell and compare it with two cations only, such as cesium and Ma only, or cesium and Fa only, to understand the function of the triple cations also. And other recommendation include future research usage of cesium cation or another effect, such as proton radiation stability and oxygen resistance. And also effect of cesium and other chemical substance would be further investigated for better stability mechanism. And the last one, regarding cesium doping in transport layer, it is encouraged for the next research to have cesium acetate as doping in ATL and mix also with the cesium cation in the active layer. So I'm encouraged for the next emerging research to combine the doping of cesium in both electron transport layer and also in active layer. And I think that's all from my presentation. I would be happy for any questions. Thank you very much. I will give it back to the committee.
We believe we want to have a question and answers, but I've noticed that here exactly 15 minutes, so it will not any question and answer for you. Is it okay, Mr. Yura? Hello, can you hear me?
Sorry, could you please use another mic, because from afternoon is, I think it's not really good.
Yeah, what? Check, how about now?
I think it's going better.
Okay, thank you so much. Yeah, I have noticed that your presentation is exactly 15 minutes, so it will no any question and answers for you. So thank you so much for your attendance, and also thank you for sharing your precious work to us.
Thank you very much.
So William, yeah, see you in another occasion. Okay, ladies and gentlemen, we will move on to the next presenter. Okay, we'll have Ms. Dita Arianti from Institut Teknologi of Bandung. She will present about the effect of cobalt gamma irradiation exposure on carbon material characteristic.
Yes, thank you.
Yeah, okay, we can hear you, Ms. Dita, so the time is yours.
Okay, thank you for the time and for the change here. I will explain about my project research. with the title is Effect of Cobalt-60 Gamma Irradiation Exposure on Carbon Materials Characteristic. For the introduction, we know that carbon has many advantages such as absorber, energy storage application in batteries, and then supercapacitor, fuel cell, biosensor, and drug delivery system in medicine. But activated carbon is usually use two methods. It's physical and chemical methods. In the physical activated methods, use high temperature and need high energy, while in chemical activation methods make chemical residue. So we try to use clean methods. We use gamma irradiation. So the objective of this research is how is effect of gamma irradiation cobalt-60 on chemical bond, which is characterization by infrared and surface area characterization by BET on material carbons. The methodology of this research is divided into 3 steps. The first is synthesis activated carbon and sodium lauryl sulfate, and then irradiation of synthesis activated carbon. In second method, synthesis material was irradiated by dose gamma irradiation 50 kilograms at cobalt-60 at irradiator facility. And the last step is characterization techniques, which is we want to see how chemical functional group and surface area characteristic of carbon materials use infrared or FTIR, and BET use quantachrome instrument. And then the result and discussion as the result of cobalt-60 gamma irradiation exposure at dose 50 kilograms on carbon sodium lauryl sulfate 50 kilograms, the broad peaks at 1,346 per centimeter decreased dramatically. This result was same agreement with the previous study about effect gamma irradiation on some materials. Peak characteristic decrease on oxygen matrix was because of radicals formation. The formation of hydroxyl and hydrogen radicals in this material system may be because reacted with surface of carbon. This is linear with Ponlam et al. At 2033. And then the result of nitrogen adsorption is isotherm at 77 Kelvin of carbon materials. So that according to physics option isotherm division of UPAC, carbon sodium lauryl sulfate and carbon sodium lauryl sulfate 50 kilograms increase proportionally to the increase of relative pressure. It indicates that carbon sodium lauryl sulfate and carbon sodium lauryl sulfate 50 kilograms lead to be type 1. The definition of a step or type 1 is carbon sodium lauryl sulfate and carbon sodium lauryl sulfate 50 kilograms had broader range of pore size distribution, which is include on micropores and narrow of mesopores. And then from BET surface area characterization, we know that carbon sodium lauryl sulfate had highest surface area because of surfactant existence. Surfactant was chemical compound prevent agglomerated particles, stabilizer, and in the formation of emulsion. We will also coat the formed particle so that it will limit bonding of the particle each other, because surfactant have hydrophilic and hydrophobic characteristics. And the development of pore happened in 3 steps: opening pores, excogitation of new pores, and micropores development. From beginning of micropores, carbon sodium lauryl sulfate became micropores because of surfactant. Otherwise, the surface area and pore volume of carbon sodium lauryl sulfate 50 kilograms was the lowest one. It happened because degradation processing of carbon from gamma cobalt-60 radiation made some pore block, so the surface area and the pore volume were decreased. And the last conclusion, based on experiment result, it can be concluded that the effect of irradiation exposure gamma 60 on decreasing of peak characteristic oxygen, which is was because of radical formation of hydroxyl and hydrogen radical in this material system, maybe because reacted with surface of carbon. The surface area and pore volume of carbon sodium lauryl sulfate 50 kilograms was the lowest one. It happened because degradation processing of carbon from 60 cobalt gamma irradiation made some pore blockade. So the surface area and the pore volume of irradiated carbon were decreased. Thank you for the time.
Ms. Dita?
Yeah, thank
Yeah.
you. Yes.
Okay. Thank you so much, Ms. Dita, for your presentation. And move on to the question and answers because we have a couple of time, I think, here. Is there any question on the floor or maybe from the Zoom related to the research about the effect of cobalt gamma irradiation exposure on carbon material characteristic? Anyone?
No, I think.
Yeah, well, actually, I have one question for you, Ms. Dita. It's maybe related to the process of your experiment because I noticed that you use cobalt gamma, right? So, is there any special maintenance during your experiments because you also deal with carbon materials in characteristic? You got my point? Hello, Ms. Dita?
Yes, yes.
Yeah. Yeah, you got my point, or you need me to repeat it once more?
Okay, can you repeat your question? I'm so
Yeah.
sorry.
My concern is about your kinds like experiment related with cobalt gamma because I have read some things like paper that
I'm so sorry.
yeah,
Your speaker is I didn't catch your question
hello.
because hello, your mic. I'm so sorry.
Yeah,
Your
let's move another mic. Okay, maybe I will go through the chat box if it's necessary to you,
okay,
Miss
okay,
Dita,
okay,
because
okay,
I have a little problem
okay,
with this microphone. Okay, thank you so much, Miss
okay.
Dita,
Thank you, thank
for
you, thank you.
for sparing your time and give us the talk for this afternoon session. Okay, ladies and gentlemen, we will move to next presenter. Wait. Okay. The next presenter will be Mr. Iwan Priwanto from Diponegoro University. However, he has confirmed to us that he cannot attend the conference, so he traveled later. And the next one, actually, we would have from Mr. Institute, but due to the health condition, so he also cannot make the presentation for this afternoon session. So we will move on again to our next presenter. He is Mr. Muhammad Harza Arbada Kalijaga from Institute Technology of Bandung with the title of the presentation PMMA bone cement with L-arginine nanofish bone nanocomplex to generate apatite formation. So Mr. Harza, are you with us? Hello?
Hello, can you hear my voice clearly?
Mr. Harza?
Hello?
Okay. Yeah, the time is yours. You have
Okay.
15 minutes to
May I share my
deliver your
screen,
talk.
please?
Please.
Okay, thank you. Okay. Can you see my screen? Okay, good afternoon, ladies and gentlemen.
Hello,
First,
Mr. Harza, we cannot hear you.
uh, can you hear me?
Okay, yeah, right now it's really clear. So
Okay,
please.
okay. Okay, good afternoon, ladies and gentlemen. First of all, I'd like to thank the organizers of this event for the opportunity that has been given. Okay, let me introduce myself. My name is Muhammad Harza. I'm from Institute Teknologi Bandung, Indonesia. I'm here today to present our study. As you can see on the screen, our topic is PMMA bone cement with nanofish bone and L-arginine nanocomplex to generate apatite formation. This research was supervised by Mrs. Eka Fianti Prajatelistia from Materials Engineering Institute Teknologi Bandung, Mr. Orka Arjasa, Ms. Nuning, Mrs. Riastuti, and Mr. Jarod from Advanced Material Research Center, National Research and Innovation Agency Indonesia. Okay, this presentation is structured as follows, which includes research background, research objectives, research methods, results analysis, and conclusion. I'll start off by the research background. According to katadata.co.id, which comes from data of the Indonesian Ministry of Transportation, in 2021, there are more than 100,000 cases of traffic accidents in Indonesia. Of this, 34% of them suffer from broken bones. The problem of bone injury has become a public health issue. One of the solutions to this problem is using bone implants. One of the components in bone implants is bone cement. Bone cement is a material used to stabilize implants and ensure even mechanical distribution from the implants to the bone. The most often used material in bone cement is polymethyl methacrylate or PMMA. PMMA is a lightweight synthetic polymer and is an economical alternative when high-strength materials are not required. The advantages of PMMA are easy to process, inexpensive, have good mechanical properties, low toxicity, inert, and slow degradation ability. However, PMMA still has some major drawbacks. PMMA poorly integrates with the surrounding bone tissue and not conductive to bone cell adhesion and growth. Another drawback of PMMA is the lack of antimicrobial activity and can overheat due to the solidification resulting from the exothermic polymerization reaction. Then, the deficiency of PMMA can be suppressed by adding fish bone waste on PMMA bone cement. Why was the NFP added? First, because of the NFP is rich in calcium and phosphorus. NFP can provide immunity to the microenvironment to promote bone regeneration. Then, the nano size has high surface area and can enhance the cellular attachment, proliferation, and adhesion of osteoblasts. Then NFP contains 60 to 70% inorganic salts and hydroxyapatite, which are good for biocompatibility and bone growth. The NFP used in this study was from salmon salarfish. PMMA NFP is then combined with L-arginine protein to accelerate the formation of new bone. The addition of arginine is able to increase biocompatibility and provide antimicrobial effects of the PMMA. Well, this research focuses on the manufacture of PMMA bone cement by utilizing NFP and L-arginine protein. The purpose of this study was to determine the effect of the NFP-L-arch addition on the particle size, morphology, mechanical properties, degradation rate, and biocompatibility of PMMA. This slide shows the synthesis method of this study. First, this study intends to determine the effect of the SDS surfactant to PMMA using the emulsion polymerization method. And then, NFV preparation was carried out using salmon salarfish. NFV samples were prepared by grinding process and then followed by milling process. The NFV samples were then dried and grounded using a mortar. The detail of the process can be seen on the screen. The bone cement was synthesized by hand mixing the PMMA, MMA liquid, NFP, and L-arginine powder. Then the mixture was placed in the mold. After curing process is complete, the samples were then characterized to see the properties of the bone cement. The characterization performed was solid content characterization, PSA, FTIR, XRD, EDS, SEM, tensile test, and immersion test. Okay, this slide shows the results of this study. Start from the solid content characterization. Table 1 shows the solid content of PMMA with SDS variation. The MMA used in the PMMA synthesis was 28% compared to the solvent. And then the polymerization of all PMMA samples produced was effective in converting MMA into PMMA. Next is the FTIR characterization. The FTIR results of the sample were compared by the structure of PMMA, which can be seen in figure 1. The FTIR results corresponds to groups in the PMMA structure. PMMA 1 SDS, 3, and 5 SDS have peaks at a wavelength of around 3,400 per centimeter. These peaks indicate the presence of sulfate in PMMA sample due to SDS addition. Next, figure 2 and table 3 shows the particle size of the PMMA samples. The data shows that the more SDS added, the smaller and more uniform the PMMA particle size will be. And then the role of surfactants in the polymerization process is to regulate and produce uniform particle size. The next is SEM characterization of the PMMA sample. SEM characterization was performed on PMMA 0 and 5 SDS. These two samples were selected to see the morphological differences in PMMA samples with and without SDS as a surfactant. Figure 4 shows that the sample produced uniform round grains. And figure 5 shows that the PMMA particles are agglomerated so that the grains are not clearly visible. It can conclude that the resulting morphology was influenced by the particle size. Okay, this slide shows FTIR spectrum of the prepared NFB. From the FTIR results, NFB samples have all the functional group possessed by hydroxyapatite, so that the structure of NFB has similarities with the head structure of hydroxyapatite. In reference, the group around 3,568 per centimeter confirms the presence of a hydroxyl group. In addition, the presence of carbonyl and phosphate groups has also been confirmed. This slide shows the SEM characterization of NFB sample. The particle size of the NFB sample was measured using PSA, and the average sizes was 757.5 nanometers with 0.527 PDI. Figure 7 showed that agglomeration occurs in NFB samples. Agglomeration causes the non-uniformity of NFB's particle size. Apart from the agglomeration effect, it can also be seen from the PDI value of the PSA results, which is quite large. The larger the PDI, the more non-uniform the particle size produced. This slide displays the EDS results from the NFB sample. EDS characterization looked at the calcium to phosphorus content of NFB. Based on the result in table 5 and figure 8, the calcium to phosphorus content of the sample was 1.65, while in human bones is 1.67. It was found that the value of the calcium to phosphor content from the NFB preparation was very close to the calcium to phosphor hydroxyapatite content in human bones. The next is the XRD analysis on NFB sample. Figure 9 shows that the peak formed corresponds with the ICDD-PDF standard. Based on the phase analysis on the Profex application, 100% of the phase is hydroxyapatite. So it can be confirmed that hydroxyapatite is formed in NFB samples. Okay, in this slide, we start to focus on the PMMA bone cement characterization. Figure 10 shows that the peak on the XRD results from the PMMA corresponds to the peak on the XRD PMMA results from reference. So the XRD data also confirms that the sample is PMMA. In the XRD results of PMMA 1 NFB, the presence of peaks in the NFB was not seen. This indicates that the structure of PMMA is not affected by the addition of NFB, and no chemical reactions occur between PMMA and NFB. The next is the results of tensile tests of the PMMA bone cement. Figure 12 shows that PMMA 1 SDS has the greatest tensile strength value. From the PSI test results, PMMA1 SDS has the second largest particle size after PMMA0 SDS. The smaller the particle size, the higher the mechanical strength of the composite should be. However, from the tensile test results, this did not happen. Judging from the results of same morphology in the previous slide, in PMMA0 SDS, the particle shapes resulting in the product are uniform and round. Then, in PMMA5 SDS, the same results show agglomeration in the particles, so the appropriate morphology could not be seen. Agglomeration of nanoparticles reduced the potential for improving the mechanical properties of nanocomposites due to the limited interfacial area. Thus, from the tensile test results, PMMA1 SDS produced the highest tensile strength because PMMA1 SDS has an optimal particle size that does not produce agglomeration. The next is the result of bone cement tensile test with the NFB and L-arginine protein addition. From figure 13, the NFB and NFBL arginine addition reduce the mechanical properties of PMMA0 SDS and PMMA1 SDS. The cause is the coefficients of thermal expansion difference between PMMA and NFB. PMMA has coefficient of thermal expansion 10 times larger than NFB. This can cause a hoop tensile stress. From the graph, it can be seen that only two samples, which is BC PMMA1 and BC PMMA1 NFBL arch, could exceed the tensile strength value of commercial PMMA. This slide shows the immersion test results from all of the bone cement samples. Figure 14 shows that all bone cement samples experience an average increase in mass after being immersed in SPF solution for 7 days. This condition indicates that apatite layers have been formed. From figure 15, we can see that BC-PMMA1 NFBL arch sample has highest mass increase rate. Okay, figure 16 shows visual observations of the samples before and after the immersion test. Before immersion test, the color of the sample was brownish yellow, and after immersing for 7 days, the color of the sample changed to grayish white. This also indicates the possibility of the apatite layer formation. The BC-NFB composite sample has more uniform apatite surface. Well, this brings me to the end of my presentation. Here is the conclusion of our study. First, PSI characterization shows that the SDS surfactant additions will produce PMMA with a smaller particle size. The same results showed that PMMA without surfactant would produce a round morphology PMMA grains, and PMMA5 SDS resulted in agglomerated PMMA morphology because the particle size was too small. Second, the FTIR and XRD results confirm that NFB has a chemical structure similar to hydroxyapatite. The PSR results show that the NFB's particle size is 757.5 nanometer. The ADS results show that the calcium to phosphor from NFB was similar with the ratio of calcium to phosphorus hydroxyapatite in the human body. Third, the addition of NFBL arch to PMMA bone cement resulted in lower tensile strength than PMMA due to the difference in coefficient of thermal expansion. The NFB L-arginine addition will cause an increase in mass after the immersion test, which indicates the formation of an apatite layer. Well, that's all I can present today. Thank you very much for your attention.
Also for your insightful presentation. And actually, your time is still have a couple of minutes. Is there any question from the audience or from the attendants in the Zoom? All right, I think you still have maybe one question for you because you still have 1 minute, and would be come from me actually, Mr. Harza, if you don't mind.
Okay.
Yeah. Do you can hear me clearly right now?
Yeah, I can
Yeah.
hear you.
Okay.
I can hear
Yeah.
you.
Yeah. Since as we know that when we talk about the experiment related to our body bonds, it's really hard to determine which one is have a characteristic that suitable with our bodies and which one is have an allergic or such thing. do you have any ideas or maybe experiments related to your previous work that this material is very can sweat with the body and the other one is cannot to be, I don't know, maybe the implant or such thing?
Okay.
Yeah, thank you.
Can you give me a couple minutes?
Yes, you have it.
Can I answer your question in bahasa?
Sure. Oke, silakan Mbak.
Oke, karena untuk penelitian sebelumnya sebetulnya untuk penelitian ini untuk kita mengetahui apa namanya suatu material itu cocok atau tidak di tubuh kita itu bisa melalui pengujian in vitro atau in vivo terlebih dahulu.
I see. Yeah.
Jadi ada pengujian selnya terlebih dahulu sebelum dimasukkan untuk atau diuji langsung ke tubuh manusia atau ke tubuh hewan gitu. Jadi harus ada pengujian in vitro terlebih dahulu. Seperti itu.
Okay. Yeah. I think that's all for your answers. Okay. Thank you,
Okay.
Mr. Harza, for your answers. And
Thank you so much.
yeah, and thank you also for sharing your fruitful work to us. And congratulations to be one of our oral contributors in the ICAMT 20 and 22. Okay, ladies and
Thank you so
gentlemen, due to the limited time, we will move to the next presenter, which will be presented by Ms. Ravina Diananda from National Battery Research Institute with the topics, the effect of steering time and the synthesis of NMC 721 using oxalate co-precipitation. So for Ms. Ravina, you have 15 minutes to deliver your speech.
Okay, everyone. Assalamualaikum warahmatullahi wabarakatuh. Now I'm right here to present my research. Now I'm right here to present my research. The title is The Effect of Steering Time in the Synthesis of NMC 721 using Oxalate Co-Precipitation in collaboration with Muhammad Fahrudin and Evi Kartini and we are from National Battery Research Institute or NBRI. Okay, for the introduction, nowadays lithium-ion batteries are becoming in the main focus research of scopes, energy and storage. And the main focus research scope with energy and storage as it provides high energy density, extended life cycles and lightweight. And LIB consumptions are forecasted to be increased, which driven by raw materials demand in EV industry and numerous industry have put technological advancements that have resulted in a vast range of diverse electronics gadgets being produced globally. And the condition has forced the lithium-ion battery consumption, in addition to their great performance in the capacity, in lack of memory, memory effects, and also life cycle and lower price and enhanced safety features. The major performance of enablers or batteries are advanced material such as cathodes, which are really crucial in the defining of the core structure, environmental impact and safety, are risk and recyclability of the battery cell. Lithium nickel manganese cobalt oxide or NMC is the most and the one of dominant battery materials because of their low price due to the less cobalt usage, high abundance, and also the stability of structure, high capacity due to the high nickel content, has stability with the manganese and long life cycle, and NMC-based cathodes when compared to LEMO2 cathodes also have the combined advantage of the transition metal, with nickel being able to offer high specific capacity and cobalt and manganese being able to provide layer structure and improved structural integrity. And based on previous research, NMC 721 is much safer than NMC 811 because Higher nickel content may lead to side reaction and also its capacity, and which cause the reduction of capacity. And then NMC 721 also has higher capacity than NMC 622 and 532. And of course, numerous techniques such as solid states, hydrothermal, sol gel, and cold precipitation were used to produce the NMC, but the most compatible for making the NMC is co-precipitation. The best method for making the NMC is co-precipitation because because it's more affordable and environmentally friendly and than other precipitant. Okay, this research will conduct NMC 721 cathode synthesized by using oxalate co-precipitation. OCP appropriate measurement of NMCs with good uniformity because of this reduced nature of the oxalate ion. And the steering time parameter was used in this study to calculate the base NMC 721 cathode result at 1 minute. Well, the parameter is 30 minutes, 60 minutes, and 180 minutes. Okay, now we had two method. Well, I'm going to explain you preparation of the hydroxide precursor. At first, we are prepare our nickel sulfate, manganese sulfate, and cobalt sulfate, and we mix together with oxalic acid as precipitate, and also we add ammonia and we mix it together until the pH reaches 6. And then the result of the co-precipitation is the slurry. It's a kind of blue slurry. And then after that, we doing filtration and washing to remain other impurities or something. And then we're drying it in the oven at 102 Celsius degree. And then we are reach Ne nickel mangan cobalt 721. Yeah. And then for the next step is solid state synthesized to LeNMC. The powder of NMC is mixing with lithium hydroxide, and then we calcination. Also, we grinding and calcifying to reach the fineness of powder, and we got our cathode material active powder LeNMC 721. This is the picture of my research recently. That's the blue one. It's a co-precipitation process, and then after we got the slurry, we dry it and we rise it with distilled water. And this black one is cathode active material. Cathode active material after calcination with temperature 800 degrees for 12 hours. And this one in the little mini cup, beaker glass. It's slurry for coating material. It's slurry mixed together with NMC 721, LeNMC 721, NMP, PVDF, and also acetylene black. And then we pour into aluminum foil at the coating film, at the coating machines, and then coating machine roll over like this one. And also the coating machine came back again, and this is the bottom is the film that coated with cathode NMC 721, and then we dry it into the vacuum oven for 1 hour, and then we cut the films into the coin cell size, and we made the battery cell coin in the glove box. So this is the result and discussion. The oxide precipitation method is employed in this study along with the steering time parameter 30 minutes, 60 minutes, and 180 minutes were the study's time intervals. What? High score plus was used to process the data via X-ray diffraction. As we can see, the error are expected For sample 30 minutes is 2.5. For sample 60 minutes, 2.6. And for sample 180 minutes is 2.6. And also the goodness of fit. For sample 30 minutes is 1.9. For sample 60 minutes is 3.3. And for sample 180 minutes is 1.4. And the crystal system, trioval is hexagonal or trigonal. And also the comparison between LENMC 721 that made by our research, and this is the lithium NMC 811 in commercial. Well, the difference is we're not the data not our research not clear splitting of 006 and 012 and 108 and 110, while the commercial is clear splitting of 006 and 012 and 108 and 110, because when they have that the clear splitting, when we got it into the XRD, more order layer hexagonal structure, it means when the split is appear on the data, it means more order layer hexagonal structure. And also on our data, the intensity 003 and 104 for sample 30 minutes is 1.134, and for sample it's 60 minutes 1.3. So it's undesirable because the commercial based on research decide that 1.2 is desirable cation mixing, but we have for sample 180 minutes 1.2, it means one of our sample is desirable cation mixings. Why our sample result like that, to be like that? It means Le plus and Ne plus have identical atomic radii. Any atoms can fill the Le layer, and this causes disorder phase development to begin, which lowers the strength of 003 diffraction peak associated with the layer structure, or even the complete loss of 003. The peak formation of the metal oxide type phase, for example, NEO. In this research, this ratio intensity 003 and intensity 104 can serve as a qualitative indicator for ion exchange in oxide layer structure. And this is a parameter for nickel mangan cobalt oxide 721. We can see the intensity 003 and intensity 104. Just only sample 180 like desirable cation mixings is 1.2, but the peaks 006 and 012 have yet to be separated. If the air value is lower, the quality of the crystal structure is higher, while the value of Ca or crystal correspond to the stability of the layered system as shown in table 2. And there is no significant difference between the three parameters of crystal or Ca or the Kc. The time value of 60 minutes is a little bit higher than that of 30 minutes and 180 minutes, indicating a more complex layering, and this element contributes to cathode materials and change electrochemical performance. And also the two powder Ca values are greater than the optimum value but less than 4.96, while indicating partial cation mixing in the powder. So the conclusion is, according to this research, the high purity NMC 721 has been effectively synthesized using the co-precipitation approach throughout the range of time. 180 minutes of stirring time produced the best synthesized outcomes among other times because the goodness of it is 1.2, which is closely to 1. And then the air value in XRD pattern has demonstrated 006 and 012 and 108 and 110 are not completely divided or split due to lower sintering temperature. Thank you.